Hey there, chemistry students. This is Ms. Ruark. We're in Vodcast 2.3 where we're going to talk about the trends of the periodic table. And, well, it's just another way to see why that periodic table is just a big old cheat sheet for you. All right, so in our trends, we have to talk about the nuclear charge. Now, we've talked about this. We just haven't called it the nuclear charge. All right, inside the nucleus, we know that it's made up of protons and neutrons, right? Positive charges and neutral charges. Well, guess what? The positive charge of the nucleus comes from the protons, and that's what we call the nuclear charge. So the more protons, the stronger the charge. I don't know if that red's really showing up. Let's see if I can, let's do dark blue. All right. So the more protons there are, the stronger the charge there is. Just a stupid little joke. Okay. Moving on. Electrostatic force. So when we did the little worksheet that talked about Coulomb's law, remember Coulomb's law was the attraction between those negative and positive charges. So Coulomb's law describes this force of attraction that's going on there. All right, and we need to know that, oh, let's go back there. We need to know what that electrostatic force or that Coulomb's law is, because Coulomb's law is going to be one of the reasons that the trends behave the way that they do. And nuclear charge is going to be another reason that the trends behave the way that they do. So what are the trends we need to know? Well, one of them we need to know about is called electronegativity. And electronegativity tells us how tightly are those valence electrons being held. Okay, more specifically, it's, let's see here, it's the pull on shared, make sure you write this down because I'm writing it, pull on shared electrons by an atom. Okay, so they're sharing electrons, and one of them just pulls those electrons in a little bit closer than the other does. Okay, so more electronegativity will pull those electrons closer in. All right, and what's the trend for electronegativity? Well, oh, one more thing. This is a calculated value. It's not something that you yourself could come up with or test in a lab. It's just something that's calculated based on an equation. Do you need to worry about that? No, you don't. You just need to know the trend. So what's the, oh, no, come back. Go back. All right, so what's the trend? Well, if you look here, it shows that electronegativity is low. Oh, not my luck, not my luck. All right. It shows that the electronegativity is low when it's blue and it's high when it's red, right? So what's the trend as you go up the periodic table? It gets stronger. As you go across the periodic table, it gets stronger, right? So what's the most electronegative element on the periodic table? Why, that would be fluorine. It is the most electronegative element. You need to know that. What are the least? Well, they would be a tie for last place, which would be cesium and francium. They both have the least amount of electronegativity. And the question could be, why? All right, well, think about it. Fluorine is got, well, it's got a decent amount of electrons and neutrons in it. It doesn't have as many as cesium and francium do, but the electrons that it does have are all located on the same energy level. Okay, they've got them all right around the second energy level, with the exception, of course, of the first two, which are on the first. All right, well, cesium and francium, they have them in the first, the second, the third, the fourth, the fifth, the sixth, the seventh. I mean, you name it, they've got electrons everywhere. Okay, and then the further out those electrons get, the less of a hold they're going to have on them. Why? Because they're further away. All right, well, and this will all make sense when we get into class. Right now, I'm just giving you the groundwork. All right, so atomic radius. What happens to the size of the atom as we go down the periodic table and across it? Well, the atomic radius, we're talking about the size of the atom. All right, and the size of the atom, if there's less energy levels or energy shells, you'll get smaller atoms, which means they take up less space. And if there's less energy shells, those, as you go across, okay, so as you go down, the size of the atom gets bigger. Why? Because you're adding more energy levels. They're getting further and further away from the nucleus. As you go across, the size of the atom is getting smaller. And the reason they're getting smaller is because you're just adding electrons to that same energy level, and those electrons are being able, the protons are holding those electrons in even closer, so there's a greater nuclear charge. You're going to hear nuclear charge and Coulombic attraction a lot, so get used to them. All right. What else do we have? We have this thing called ionization energy, and it is the energy that's needed to remove an electron. Now, you can have the first ionization energy, you can have the second. Guess what? You can have the third. Hey, you can even have the fourth, and you can keep going. Okay? You can keep going. So this would be the energy needed to remove the first one. This is the energy needed to remove the second one, the energy for the third, the energy for the fourth, and so on and so forth. All right, if you have a higher ionization energy, it's going to be harder to remove an electron. So look here, the ionization energy is going to increase, or the energy needed to take an electron is going to increase as you go across the periodic table. Okay, it decreases as you go down the periodic table. Okay, why does it decrease as you go down? Because those electrons are getting further and further from the nucleus. There's less nuclear charge. Not less nuclear charge, sorry, there's less Coulombic attraction. There's less pull on those electrons because they're further away. Well, as you go across the periodic table, they're not further away, they're closer, and so there's greater Coulombic attraction. All right. Cations are typically going to have a lower ionization energy than the anions will. And the anions are going to have a higher ionization energy than the cations will. All right. Shielding. So what in the world is shielding? Okay, well, shielding is something that affects the size of the atom. All right, so in Coulomb's law, we talked about the attraction between the protons and the electrons. And that attraction, that Coulombic attraction, is what pulls... Hold on, gotta sneeze. So sorry about that. Okay. The Coulombic attraction is what pulls those electrons in towards the nucleus. Well, as the energy levels get more and more, the Coulombic attraction gets less and less. But guess what? The Coulombic attraction gets less and less because there's more electrons on the inside. Okay, so if we're adding, here we got our nucleus, and we've got all these, we keep adding all these energy levels. And as we add these energy levels, we've got electrons out here. Ooh, they kind of melded into one another, didn't they? All right, we've got electrons out here, and these electrons are being pulled on by the nucleus. But guess what? You also have all these electrons in here. And I don't know if you remember me saying something about this, but I did say that likes repel. And guess what? All these electrons on the inside are pushing those electrons out, and they're saying, ew, get away from me, get out of my space. I said, Mom, he's on my side, right? Yeah, you all know about it. The struggle is real, right? So, all those electrons on the inside are pushing those outside electrons away. They're repulsing them. They're saying, go away. And so that nuclear charge is not able to pull. The Coulombic attraction isn't as great, and it's because of shielding. So the electrons, or the inside electrons, get in the way, and they shield or repel the valence electrons. Remember, valence electrons are outside electrons. All right. Which has more influence, nuclear charge or shielding? Well, guess what? As you go down the periodic table, the nuclear charge gets greater and greater and greater, but so does the size of the atom. And if nuclear charge was really the one that had the most control, then the size of the atom would get smaller as you go down, but it doesn't. So what has more influence? Shielding. Shielding has much more influence. All right, and this is just a chart to show you the trends for atomic radius, electronegativity, and ionization energy. And then the last thing that's on here talks about metallic character. So we have our staircase here. And our staircase here is a wonderful staircase, I know. The staircase here splits your metals from your nonmetals. So over here you have your nonmetals, and over here you have your metals. All right, well, guess what? The further and further you get away from the staircase, the more the further you get away from the well, let's see this. As you go this way across the periodic table, it becomes more and more non-metallic in character, and as you go this way on the periodic table, it becomes more and more metallic in character. Okay? And then there's one last thing that we have to talk about. It's called reactivity. Write this on your paper. All right, reactivity. Guess what? I'm going to ask you questions about which element is more reactive, and you're going to have to be able to tell me this. So pay attention. All right, the further from the staircase you are, the more reactive the elements become. Write that down. I'm going to say it one more time. If you didn't get it, rewind it. The further from the staircase... Okay, I thought I was going to say it one more time. Let's try that again. The further from the staircase you are, the more reactive the elements become. Okay? Close to the staircase, little reactivity. Further from the staircase, more reactive. The only exception to the rule is the noble gases. Why? Because they are unreactive. There's always an exception to the rule in chemistry. Y'all should know that by now. All right, I think that's about it, boys and girls. Yeah, here's something for Lady Gaga. All right, I'll see you in class.